Hi guys, we're going to work on page 22 and we're going to review potential energy diagrams again. So first I want you to see if you can label all of the parts of this diagram. Anything that you remember. Pause the video. Can you put in what some of these parts are called? So if you remember the beginning over here, we've got the reactants and the end of the products. So the middle of the reaction, where it's kind of halfway, is called the activated complex. Then we can measure up the height of this hill. So from the reactants up to the activated complex is called the activation energy. And then if we measure between the reactants and between the products and kind of ignore that hill, that is called the heat of reaction. So you'll notice that this graph is a little bit different because now we've added some actual numbers down the side. And so now we're going to actually start calculating some of the parts on this graph. So let me show you what I mean. So we are able to calculate the activation energy. So here's the activation energy. So remember, we measure between the activated complex and between the reactants. So in order to calculate what is the actual activation energy, you're going to subtract those two things. So you're going to do activated complex, I'm going to abbreviate, and minus the reactants. That will give you the actual value of the activation energy. Now we can do the same thing for heat of reaction, and that is over here. So remember, heat of reaction falls between the products and the reactants. So same thing to calculate, we're going to do products minus reactants. Now the thing you need to be careful of is the order does matter. So you must do activated complex minus reactants. Don't mix them up. Same thing, you have to do products minus reactants. Don't switch the order. Okay, so let's do a little practice with the graph that you've got. So if I want to know activation energy for the forward reaction, so I want to know between this activated complex and the reactants, right? So our formula is activated complex minus reactants. The activated complex here is at 450 kilojoules. Then we're going to minus the reactants have 200 kilojoules of energy. So if I subtract that, the activation energy is 250 kilojoules. So we just subtract. Now, if I want to go reverse, remember that that means that I'm going to do activated complex, and these will become the reactants. So same thing, we're going to subtract the same two things. Activated complex is still at 450. And now we're going to subtract. Now my reactants are over here because we're going backwards, and that's at 350. So subtract those two, we get 100 kilojoules. That tells me that the forward reaction has a larger activation energy. And that makes sense, doesn't it? That means that this hill to go up here is much bigger than this hill. And now we actually calculated those values. Okay. Now let's try to calculate delta H, remember? If you're not sure of what that symbol means, this is a way to shorten for heat of reaction. Okay, so the formula for that, we're going to do products minus reactants. So if we're going forward, here are products, here are reactants. Be careful of the order. Okay, so products, 350 kilojoules of energy minus reactants, 200. So the delta H there is 150 kilojoules. But if I go in reverse, I'm still going to do product minus reactants, but their locations are going to flip. So what that means is this is now the product, and this is now the reactants, and we would go this direction. Okay, so that means my products are at 200, and the reactants are at 350. Now you'll notice when we subtract, we're going to get a negative number, and that's okay. So it's negative 150 kilojoules. So notice that the delta H's, the heat of reaction, are the same value, but one is positive and one is negative. That's why the order matters, that you subtract these really carefully. Okay, this is going to help us figure out what's endo and what's exo. So you should know, hopefully you remember, endo is when the graph goes up because you add energy, and exo is when the graph goes down. Another way that you can figure that out is endo will always have a positive delta H, and exo will always go negative. So let's compare this for both. If I look at the beginning and the end of this reaction, notice that it went up. That means I added energy. That's what the delta H measures. So see how I have a positive number here? I added energy to the reaction, and that only happens when we have endothermic reactions. Okay? If I look at the reverse and I go backwards, then here would be the start of the reaction, and here would be the end, and notice that it goes down. That means energy went out or got lost. That's what this negative sign right here means. So whenever you have a negative delta H and your graph has gone down, then your reaction is exo. Okay? Lastly, we talked about these reactions having or being affected by catalysts. So let's draw a catalyst in. So the point of a catalyst is the reactants will start at the same location, but the activation energy gets lower. So it's a smaller hill, and then you still finish at the same location for products. So what that means is the parts that are changed, notice that the activated complex isn't as high. So the first thing that gets changed is the activated complex, and that has been lowered. Because we changed the activated complex, that's a part of how we calculate the activation energy. So activation energy is also lowered. Remember, the reason that we do all of this, it is much faster to climb this little hill than to do the original big one. So the reason that we have a catalyst and the reason why we care is this makes the reaction go faster. Okay, we've created a smaller hill to climb, and that's a whole lot easier, and you can do it quicker as the reaction. So now it's time for you to do a little bit of practice. Here's your diagram below. First, I want you to take a minute, see if you can label all of the parts again, then try some of these questions and come back and we'll compare together. All right, so on this diagram, you've got reactants over here, products over here. The activated complex, remember, is the middle. And in between the activated complex and the reactants, that is where your activation energy is. Okay, I'm going to abbreviate so it all fits on the diagram. I can also measure between the products and the reactants. That is the heat of reaction. So now let's check in. Here are the answers for the questions that you should have had. If you have something different, see if you can figure it out, but if you need help, just come talk to me. Next, what you're going to do is a little bit of practice on your laptop, so check the link so you can get to work.